These are the solutions to homework set number 12 for ECE 341 random processes. This homework set looks at student t-test with a single population. Now the first problem is looking at 6-card stud. In 6-card stud, you're dealt a 6-card hand. You take the best 5 cards, and that's your poker hand. We calculated the odds of getting a full house in 6-card stud, and the odds were 815 in 100,000 hands. Let's see if that matches up with the Monte Carlo simulation. With the Monte Carlo simulation, what you do, this is back from homework set number 2, I deal out a 6-card hand. I then sort the cards, check to see if it's a full house. If I have a 3 of a kind and at least 2 of a kind, gives you a full house. If so, count. Repeat 100,000 times. So when I run that, like here I got 808 full, or 781 full houses. Run it again, 772 full houses. Every time I run it, I get a different answer. Suppose I ran that program 4 times and got these 4 results. From this, what are the odds of getting a full house? Well, I can't tell the odds exactly, but I can give you a confidence interval. So given the data, I can find the mean, find the standard deviation. In this case, I'm actually looking for the population's average. So since this is a population question, I divide by the square root of n. Then the 90% confidence interval is go left and right, 2.355 standard deviations. This guy right here is the t-score for probability of 0.05, that's 5% tails, with a sample size of 4, meaning 3 degrees of freedom. So what you get is this graph. Based upon my data, this is what the actual mean is, the probability of getting a full house in 6-card stud poker. Here's what I calculated. Based upon this one, it kind of looks like my calculations are wrong or the program's wrong. But that's with a sample size of 4. Every time I run this, I'm going to get a different answer. So let's try that again. Suppose I ran that program 20 times. Now, what's the confidence interval? So here's the same approach, same data, or same procedure. Find the mean, find the standard deviation. In this case, I divide by the square root of n, and it's 20 in this case. My t-score, with a sample size of 20, meaning 19 degrees of freedom, is 1.72. So go left and right, 1.72 standard deviations, and this is what the PDF looks like for the probability of getting a full house in 6-card stud, based upon my data. And the calculated odds are right here. That lies in the middle. So that gives me some confidence that maybe the program's right, maybe my calculations are right. Calculations are probably right because this is just combinatorics. And that's probably dead on. The program looks like it's probably correct also. So far so good. Harder problem. 6-card draw. Now in 6-card draw, you are dealt a 6-card hand. You then discard cards, draw new ones to replace them, and check to see, did you get a full house after 6-card draw, after you draw the cards? That's actually pretty hard to calculate. So what we had to do is we had to make some assumptions, such as when I discard cards, I actually shuffle them back in the deck, because otherwise it changes the probability of getting 3 of a kind. It's about right, simplifies calculations, but should be close. So when we did that, I calculated I should get 3570 full houses in 100,000 hands. Does that match up with the Monte Carlo simulation? So with the Monte Carlo simulation, I'm dealt a 6-card hand. I then check to see what kind of hand I have. And based upon that hand, if I have 3 of a kind, I'll throw out 3 cards, draw 3 new. If it's a 2-pair, I'll throw out 2 cards, draw 2 new. If it's a pair, I'll keep the pair, throw out everything else. High card, keep 1 card, discard the other 5. Now look at your hand. Now is the resulting hand a full house? So if I run that, this is 6-card draw. If I run that 100,000 times, I get a full house 825 times in 100,000. Try it again. $862. Okay, and so those numbers do not compare to the calculations at all. So, checking my program, I forgot to sort the data afterwards. So, trying it again. This is, I'm dealt 6 cards, determine what my hand is, throw out the cards that don't match, draw a new hand. And when I do that, I get a full house, 4952, 4782, 4911, so on. Calculations for 3570. So, anyway, if I have these numbers right here, what is the confidence interval? So, to do that, do the same procedures before. Here's my data, find the mean, standard deviation, gets my confidence interval. It says based on data, that's the probability of a full house. And it doesn't really match up with calculations. If I have a larger sample size, repeat, I get the mean, standard deviation, doesn't really match up with calculations. What that tells me is that either the program is wrong or my calculations are wrong. It could well be that in the calculations I assumed you put the cards back in the deck. That might actually affect the answers. So anyway, something's wrong either with the simulation or the calculations, could be both. Okay, so go on to the next problem. Next problem, if I go to this website, kind of a fun one. Yep, got to be connected with the web to do that. It'll sit there and measure your reaction time. Okay, so here's the game. When you click, oops, try again. I wait for the light to turn green. When it turns green, I click the button. 248 milliseconds, try again. 223 milliseconds. So collect some data. So when I ran it, here's the data that I got. From that, find my 90% confidence interval. So again, find the mean, standard deviation, go left and right. In this case, I'm not dividing by the square root of n. This is the difference between populations and individuals. If I say an individual, that would mean the next time I run the experiment, what's my time going to be? That's an individual. In that case, I don't divide by the square root of n. If I do populations, I'm going to say I do have an average. What is my average time? There I would divide by square root of n. So here I'm doing individuals, so I don't divide by square root of n. There's my 90% confidence interval. Go left and right, 2.35 standard deviations, and this is the t-score for sample size of 4, 3 degrees of freedom. Problem 7. What's the chance that my reaction time is less than 200 milliseconds? So this is going to be individual or population. The probability that my next trial will be less than 200 milliseconds is you take the t-score, distance of the mean from the standard deviation, distance for the mean from 200 in terms of standard deviations is 4.67 standard deviations away. Convert that to a probability, and it is 0.9% chance. That'd be for my next trial. If I wanted to know about my population, I do have an average reaction time. For the population, or my actual overall average, I do divide by square root of n. The bigger my sample size, the more I know about my actual average reaction time. So here I take sample size into account, and 200 milliseconds is 9 standard deviations away, basically saying not happening. So that is homework set number 12 for ECE 341.